welcome to the Bode Aquarium at Scripps. My name is Nigella Hilgarth, and I'm the Executive Director of the aquarium. And it gives me great pleasure tonight to welcome our speakers. Tonight we have two speakers, Warren Smith and Jerry Bode, Senior Curator and Curator Emeritus, respectively, of Scripps Institution of Oceanography's geological collections. Warren Smith came to SIO in 1967 at a time when plate tectonics was dominating research in the geosciences. A very exciting time when people were beginning to understand how the Earth's crust moves and how the continents interact with one another over time. So Warren is a geologist by training and began his career at SIO working with two renowned geoscientists, Bill Maynard and Tom Chase, on mapping the ocean floor of the North Pacific Ocean, and then working with Bob Fisher, mapping trenches in the Indian Ocean. And in the early 70s, he went to work for the Deep Sea Drilling Project as a scientific illustrator, and then he went to the Geophysical Data Center working on the evolution of mapping technology, and then he joined the collections at SIO in 1990 and has been curator there ever since. Now, Jerry came to SIO in 1968, and he worked as a geochemist, studying, not surprisingly, the chemistry of the oceans. And he joined the Deep Sea Drilling Project in 1970 and worked his way up to the Deputy Logistics Manager. That meant he was in charge of all the seagoing technicians, both shipboard and at the shore-based labs, which is actually a huge responsibility. And in 1984, he became the curator for these collections of the Deep Sea Drilling Project and the ODP project. And he retired in 2005. I just want to tell you explain what Deep Sea Drilling Project is. I know you'll hear a lot about that in the lecture. But it was when the major US oceanography institutions joined forces and started an immensely ambitious project to look at the rocks beneath the world's seafloor, which covers over 70% of this planet. So a very exciting and very ambitious project that discovered a lot of very exciting things that I'm sure you'll hear about. But what that meant was there was an enormous number of cores that were collected from that, and I believe SIO Collections has over 300,000 different specimens, over 6,000 cores. And that's a huge responsibility to collect and to curate, because it's used not only as educational material, but as scientific research. For example, at a time when we're particularly worried and concerned and want to learn about climate change, these sediment cores can tell us a lot about the past history of the Earth's climate. And so they're an enormously valuable resource, rather than having to rush out and take more cores of the ocean sediment. So now there are still expeditions doing that, but they don't have to reinvent the wheel, as it were. So now it gives me enormous pleasure to ask tonight's speakers to come up and talk. Thank you.
Good. I'm going to attempt to give you, in a very short period of time, kind of a 100-year history of what we've been doing at Scripps in terms of collecting geological samples. And in the Scripps collection, which is slightly different than what Jerry Bode will talk about in a little bit later, this is a collection where we have both cores and dredges. That is to say, we have soft rocks and hard rocks. So I will show you a few examples here. On the diagram, you can actually see some of the spots where we have collected. We've had ocean stations, and obviously we do a little bit more in the Pacific Oceans, here and over here, than we do in the Atlantic, although the Indian Ocean has received a good bit of our attention as well. The history of the Scripps Navy is pretty interesting. There was one period of time in the 60s when we supposedly had the 9th largest Navy in the world, counting all the nations. So it was interesting. So very early on, we had a ship, one of the earliest ships in 1907, the Alexander Agassiz, actually a sailing vessel, and we did a good bit of work from that. As we move on in through the 1900s, in the middle part of the century, This is the ship known as the Scripps, and this is actually Roger Revelle standing there doing some water sampling just on the starboard side of this vessel. And then finally, named after Roger Revelle, is the full-on research vessel, which is probably the second vessel that Scripps has ever had that was actually designed from the keel upward as being an oceanographic vessel. A lot of our ships were either sort of donated to us or we got them from the Navy, and so our Navy has had a varied history in the past. The first ship that I sailed on is this one right here. Incidentally, this shows our staff and so on, but I like to talk about the Horizon because this was a favored ship, and many of us liked it. You can notice here that it's only 143 feet long, so it's quite short. It's basically an ocean-going tug. But nevertheless, we got an incredible amount of science from this ship, and it did several round-the-world trips. And the quote that I give you here is always, as far as I know, a happy ship. That's from Bill Menard, and he actually wrote a little article. And if you are interested, it's an SIO reference paper in 1974, number 3. And somebody, if they're really interested in looking at this online, I'll be glad to give you this URL. I guarantee you can't reproduce that right off unless you've got a really fast memory. When you go to sea, it's radically different than what we're doing right now. Everything's very stationary, and you got to imagine if this room were on board a ship, we would all be doing this sort of thing, you know. And everybody, it's just perfectly normal because you have to keep upright as much as you possibly can. Okay, this particular set of photos that I'm showing you is from just last February down in the Southern Ocean, and this is the austral summer. And yet we're getting 30-foot waves there, and you can't really ever take a picture of how rough it really is when you're on board. But I'm just trying to give you an indication. This is the bow of the boat that's just being buried under a wave right in that photograph. You can see the list here, the tilt off as the thing is going. This is actually looking aft, so this is the trail that we're making as we go through, and it's kind of a meandering trail. I have to tell you about this one. This is my favorite expedition. We did a trip leaving Tahiti, and we headed south. Tahiti, of course, tropical, and we were all doing the bathing suit thing and so on, and doing a little snorkeling and whatnot. You head south and you get into really cold waters. This is a 56, kind of a cartoon trying to imitate what does a 56-degree roll look like. When the ship rolls 56 degrees, you do that and you touch the floor. And then you do it on this side and you touch the floor. So it's incredibly unstable in a sense. And yet we're able to get some pretty good science out of the whole thing. There's an old sailor's maxim that says below 40 degrees latitude there's no law, below 50 degrees latitude there's no God. And that's pretty much what it felt like at the time. We did not run into, but we saw and avoided several icebergs on this particular trip. And we finally made it around the Horn. But it is always, this Drake's Passage is always a tumultuous kind of place. Some of the things that we do in our collection, one of the major things, is dredging rocks, okay? And this is, in fact, a dredge box, a dredge bucket, sometimes called, with a chain bag behind it. It's really simple, sort of what I always call low technology. You just lower the thing to the bottom and drag it along, and it fills up with rocks, and you pull it back up. That's very, very simplified, and it oftentimes is very much more involved than that. This is just emptying one of the dredges onto the deck. You just hook a chain on the cable and flip the thing over. Everything on board ship that we do in terms of dredging and pretty much coring as well, everything is very heavy and massive. What I wanted to do was show you some of the big bolts that they have to anchor some of these things on, but I couldn't find any good photos. So just take my word for it. It is, in fact, a heavy thing. What are some of the rocks that we collect? I actually have, I think, all of the ones that are listed here. I have some basalt up here on the front table you can take a look at later, and some chert, and some manganese nodules. As a matter of fact, this manganese nodule, this very one, is probably the largest manganese nodule that was ever collected, and we got it by accident. We were actually doing a water sampling device, and the story that I like to tell, and it may or may not be true, that the guy running the winch went off and got a cup of coffee, and he put too much cable on the bottom of the ocean, and then when they started reeling it back in, it snagged this big manganese nodule. I've actually got a couple of little cartoon drawings of that thing up here on the front. You take a look at it a little bit later. So manganese nodules are one of these precipitate things, and you can see the concentric growth right here in this particular photograph. This is a kind of common size that they occur. This one that you see in the box right here is quite large. The basalts, of course, come from the spreading centers, the areas where the plates are moving apart and we're creating new molten material. It comes to the surface and in contact with cold, cold water, but it itself is thousands of degrees in temperature. So it's an instant cooling, and you will see these pieces that I've got up here on the table, they have a glassy coating on them, a glassy rind. One of the magic places, in my opinion, that I think, and Bob Fisher, who happens to be here today, he and I have worked a good bit. He's done the work, and I've just been able to go along for the ride. In the trenches, it's a very unusual environment. The trenches are over 6 miles in depth. And one of the stories that you can think about to kind of set this in perspective in your mind, Mount Everest is on the order of 29,000 feet tall. You could take Mount Everest and set it in one of the trenches, and it's covered by at least a mile of water, more than a mile of water. So these things are incredibly deep. And how do we get the dredges again? We've got those buckets, and you lower it down on a wire, but 6 miles of wire, I mean, that's like from here to Pacific Beach. You know, and you're trying to pick up a rock on somebody's corner, lot. It's pretty difficult to do. And I don't want to make light of it, because what we've recovered from this trench work is some amazing rocks, and they're very, very unusual. They're really high temperature minerals that have solidified under very high temperature, high pressure conditions. And so what we think about these, the interpretation is that these are in fact what they call mantle rocks. That is the part under the crust, and these rocks then represent what that almost the inner parts of the earth are made of. This particular one right here was collected in the Tonga Trench, and it's this beautiful olivine green color, and it's known as a rock, is known as peridotite, and there's actually a gemstone called peridot, some of you may know. It's a nice green color. It's the same mineral. Olivine is the mineral, and this particular large one that you see in the upper right here is actually this rock sitting right here, and I've got more information than you ever wanted to know about it right there on the front. You're welcome to take a look at that. It's actually called a Hartsbergite, or a myelinitized Hartsbergite. The people who study rocks seriously are petrographers, and they have a penchant for doing incredibly long and involved names on the rocks. And there's a lot of argument. This may be a Hartsbergite to one petrologist, and it'll be a peridotite to another one. So there's a lot of controversy, but nevertheless, come up and feel this rock at the end. You can feel how smooth the serpentine is. This is an unusual event that happened last April. And we had some ocean bottom seismometers, and they are in fact just devices that we set that measure earthquakes and any other kind of movement. It can be a volcanic eruption, it could be any kind of noise making an earthquake could cause these things to register. And these seismometers that we sit on the ocean floor, this particular one is sitting on some of this volcanic lava right down near this 9 degrees north on the East Pacific Rise. And there was a group of them, 8 of them in particular, it says right here, they were apparently buried and disabled. These ocean bottom seismometers cost around $30K per, and so it's a fair chunk of money that we could not return, because the interpretation is that they've been buried and they can no longer release themselves from the bottom. They have a lot of weights on them, and the weights are knocked off by a radio signal, and then they pop back to the surface. But we did get back a piece of the rock, and that's this right here, and this is some of that glassy basalt. So this rock right here is probably the youngest rock that any of us will ever see or have ever seen, unless you're standing right on a volcano and see it erupt. So this is an interesting geologic, very recent kind of phenomenon that has just happened along the East Pacific Rise. Okay, how do we store our rocks? This is the Dredged Rock building, and it's up on Seaweed Canyon, which is just over the hill from us here. It's a large metal building, and it is literally chock full of rocks. This is a view down one of the aisles where you can see on both sides these racks go to about 16 foot in height. And each of the dredge boxes is exactly this. Is one of the dredge boxes sitting on the table here, around 100 pounds. We try to limit it no larger than that in terms of weight. Now when we get to the cores, they actually are kept in refrigerated D tubes, and we call them a D tube. Okay, it sort of looks like the letter D, and you can slide the cores into it. I have on the table over here, Jerry has brought and set out one of the empty tubes so you can take a look at that just to see what it is. But that's what you're looking at, is the ends of those tubes, and inside those tubes are the sediment cores. We keep them at 4 degrees C to try to minimize any mold growth and so on. Try to keep them as close as we can to the pristine environment from which they came. This is the technique right here. This is actually 4 stages. It's a gravity core, a piston core, in 4 stages. So this is lowering, this is when it hits the ground, this is as it's completely penetrated, filled with sediment, and then it gets brought back to the surface. So I'm going to see if we can show you the movie now. Well, here we are at this point. So this again gives you a heads up on where the trigger core is, the piston core, and there's loose wire right here at the top. And what that allows is, this is triggering this mechanism right there, allowing this then to free fall. This is about a ton of weight sitting on top of this, because you want to drive this this hollow tube, steel pipe, you want to drive it right into the sediment. And sitting right at the surface is, in fact, and I've got another slide that'll show that in a minute. Okay, here comes the cartoon again, and you can see it going bang, bang, bang. And I'll see if I can stop it here. This is the second thing I wanted to show you, is the actual parts that make the thing up. Okay, so we have, at the first point of entry here, you have a nose cone, and it's a tapered cone, and I've actually got one sitting right here on the table. You can take a look at that. Inside it is a little core catcher. It's a little flexible fingers. It's open when it's going down, and then you get a little pressure on top of it, and it seals it to close, keep the sediment in place. Again, this is pretty low-tech kind of stuff, you know? It's almost like piston coring has been being done since the 1800s. This is the piston itself, and again, here is the coil of wire. We're going to run this little cartoon again here, and I'll just show you. I think we'll just let this one run to completion. Okay, you can see, once again, repeating, and this is going to penetrate all the way. The blue thing right there is the piston. Notice this is a taut cable now. This means that the technician who put this thing together on board ship did his measurements exactly right, and this is the perfect thing that you would like to get. One good core. The piston still sits at the surface. And you can see, well, I've got 2 phases right here. The first showing that right before this core has penetrated full length, and this is one that's showing that it's basically penetrated, and you can see the sediment inside the core then. Yep, that's good. Some shipboard shots. What does it look like when you're doing this on a rolling ship again? It's really tricky. Here is the weight stand on the far end. That's the ton of weight. Here's the long pipe, and we're running it off the starboard side of this boat, and it will be then rotated into a vertical position and then lowered into the sea. We do 4 major types of coring: piston coring, gravity coring, and this was the one that I showed you. It's also used as a trigger in conjunction with the piston core. Then we do box coring, and the difference there is that it's just a steel box without a bottom, and it gets dropped into the mud. The depth is only on the order of 50 centimeters penetration. So we're not looking for great depth in this case. We're just looking to see if what we can find in the way of a larger area right at what was called the mud line, the water and sediment interface. Okay, and then the final one is a dart core. Not surprisingly, it looks a little bit like a dart. The idea here is merely to drop this now on a hard rock, and you're going to chip that hard rock. And of course, the tube on the end there is filled with surfboard wax, and it captures all those little fragments, and then you pull it back up. The geochemists love this. It's really fast. We can run these things down full speed of the winch right to the bottom and back, so you can do a turnaround in like less than an hour, depending on the water depth. But you can get a lot of material back, a lot from the geochemist sense, because from a volcanic eruption, and you guys will see if you get a chance to take a look at some of these rocks here, that this fragmented glass on the upper surface is actually a frozen image, as it were, of all of the chemistry that was in that particular eruption. If you sieve the sediment in the cores, you end up with some amazingly unusual looking critters. And this first one that I want to point out, that is a radiolarian right on the end to give us a sort of human scale to the thing, sitting right on the end of the needle there. And this is one of the larger ones. They get quite a bit smaller than that. Okay, this is a 4am, 2 4am photographs right there. This is a diatom and some what are called the smallest of the critters. known as nanofossils, to be short, as a shorthand way of saying it. Coccolithophorids is one of the things. But these little individual plates on this spherical shape are exactly what you're seeing in this photograph here. SEM photos, that is scanning electron microscope photos, are needed with really thousands of power magnification are needed to actually study these. They're so small. The little comment here is thousands of those would be on the end of a pin head. This is one of the interesting things. Nigella mentioned a point about our interest in the climate and what's happening and how we use sediments and the ocean, studies of the ocean, to determine what's going on with our climate, and particularly paleoclimate, that is, climates in the past. This particular core on the left is in fact a lake core. These are varve deposits, and you can see the two dates, 2001 and 1957. And so these represent a little bit like tree rings. So they're seasonal deposits, basically a light colored one and a dark colored one, represents 1 year. So that particular indication of looking at varves, and that it is in fact a record or a journal of what has happened on land. Every time there's a storm, it rushes into the lake and you get it deposited. This particular core here has an interesting story. It was actually collected in the Santa Monica Basin, just off the coast of Santa Monica. You could have seen the ship collecting this. It was that close to shore. And it's difficult to see because this one has degraded over the time, but there are a series of horizontal lines or layers, varved layers in this as well. They're not as clearly defined as this one. But this has been dated. This is the 0 line here. And this is the 200-year mark at about 24 centimeters deep in this particular core. An interesting study was done by some of the geochemists here at Scripps, and one of the ideas that they thought about was what was going on in California 200 years ago. Pretty minor population, no automobiles, no freeways, not a lot of smog, not a lot of pollutants getting into the ocean environment. So if you look at an isotope like lead, which it turns out was used in gasolines, you can begin to plot here at sort of at the 200-year mark, sort of a 0 amount, and then as you go forward, you know, as we start increasing our use of gas, that curve just goes upward and upward. Then about 20 years ago, as it says down here, through legislation, it was insisted that we use unleaded gas, and that curve just drops off. So looking at sediments in the ocean collected offshore, we can actually see some of the things that we've been doing to our own environment. So that is, in fact, the anthropogenic record or journal. One of the current projects going on right now is in the Venice Lagoon, and I am involved with several of the different scientists that are using it, and we have some of the cores from this. And it's one of those typically oceanographic projects in that it involves a range of scientists. The biologists are looking for bacterial DNA in the lagoon sediment. The chemists are looking for heavy metals and pollutants. Geologists, as is Justin doing right here, is actually looking for shell and wood fragments that can be dated, and we use a carbon-14 dating kind of method to find out what's going on. We expect the sediments to all be quite recent because it's a very shallow area in the lagoon. And then the climatologists, of course, are putting all of this information together to see what they can come up with and what has been happening in our climate in recent years. And then I finally have gotten to this the news break. Just this last Thursday, I got to hold my hands on this movie, and we need to fire this guy off. Yes, there it goes.
This animation illustrates the launch and recovery of a new seafloor sampling system under construction at the Woods Hole Oceanographic Institution. Handling of the massive core is enabled by numerous purpose-built hydraulic devices, the first of which transition the system from horizontal to vertical. Once the launch lines are retrieved, the core is swung to the center of the stern of the vessel for more rigging operations. Next, the release module is attached. In this process, the long core is connected to a powerful winch that will lower the device to the seafloor. The winch is spooled with a high modulus synthetic rope, which has a brake strength of 180 tons. The rope is more than 4 miles long. In order to protect the structure of the ship, the coring load must be transferred to a stern sheave specially installed for the project. The foundation of this robust centerline sheave rests on the vessel's keel. Rigged this way, the exceptional forces that will be created by the coring process will be offset by the entire displacement of the vessel with no compromise to its stability. The core system is then lowered to the seafloor. At full ocean depths, this will take about 2 hours. Once near the bottom, an altimeter will be activated to sense the distance to the seafloor. This data is sent back to the ship by an acoustic modem, and when the proper height off bottom is reached, a release command is sent, and the core falls freely and penetrates the sediment. The core's 30,000-pound mass drives the barrel into the soft seabed. An internal piston aids the recovery of an undisturbed stratified sample. 30 or 40 tons of pull may be required to extract the core from the seafloor. The system then returns to the surface. The release module is now separated from the core, and before it can be recovered, the weight of the system below must be taken by a winch at the top of the A-frame. This allows the modem dish to be decoupled and secured on deck. From this stage on, the recovery process is a mirror of the launch. The transom davit is swung into position to capture the core. This process is eased by closing the davit arm around the pennant rope. The core head is then hauled upward into the capture system, where it is latched in place by automatic pawls. To finish the recovery operation, the core is swung back to starboard, and 3 recovery clamps are suspended into position, and the synchronized davits work together to retrieve the core to horizontal.
We'll go on to the next, and I believe this is the last one, and the obligatory sunset. This shot was actually taken down below sea level, because I was raised below sea level, and over in the desert by the Salton Sea. It reminds me of a lot of sunsets I've seen at sea, though, so I thought I would include that. Good. Thanks very much.
The deep sea drilling project actually is that if I had more time, I could give you a little more colorful description on the genesis of the program, but it was started in 1968 with one of the main objectives to prove or disprove the seafloor spreading. And it was going to be an 18-month program, 9 cruises of two months apiece, and within 3 legs at the most, they had proved the idea of seafloor spreading. But what was amazing was what they discovered in terms of when they brought up the sediments. They had never recovered deep ocean sediments before to the depth that they had. And the idea that so much of the Earth's history was tied up there is that it suddenly said, this is a good program. And obviously, they still think so because we're still going strong. Is that it continued as the deep sea drilling project up until 1983, at which time then the management was transferred to Texas, and it became the ocean drilling program, and it continued as ODP until 2003. And we came to prove seafloor spreading, and we discovered so much more. Not that the program itself solved all of the problems, but they were key to the understanding. Science is a mosaic of people working together, and the project was a central part. It helped tie things together. The deep sea drilling project used the Glomar Challenger. At the time, it was called the best floating laboratory going. By the end of the program in 1983, it was so outdated that it ended up in a scrap heap in Brownsville, Texas. It was a 400-foot ship, and hidden behind over there is the lab stack. And when the ocean drilling program started up, we ended up with the JOIDES resolution, and there's probably 5 times more lab space on the ship. The interesting thing is that when we first started out, I can remember on my first full cruise of Lake 104, they said, we have so much room we can't possibly use it all. Well, guess what? We ran out of room, and now we're trying to extend the ship another 30 feet. This is the combined site locations of both the deep sea drilling project and ODP, and you can see that we have pretty much covered much of the oceans. Now, in this area in here, I don't know whether it was lack of scientific interest or if the weather is so terrible that it wasn't worth drilling. I was on one of the cruises right in here, and I can assure you that I don't want to go back. They have drilled some sites since this was made, but you wouldn't be able to tell where they are. Recovering a core, comparing the 2 ships, recovering the core. Here you see the pipe being broke to recover a core on the Challenger. Notice how much space you have here. Here on the resolution is that the space is almost completely gone. It is almost all mechanized. Compared to the Challenger, most of it is done by mechanical efforts. Now, this is yours truly right here, and I guess everyone needs to have an experience, but we think that after 30 some odd years we have experienced everything. Well, we ended up off the coast of Australia, and we hit hydrogen sulfide gas. And we've hit hydrogen sulfide before, but you know, after 3 cores, you're past the thing, and then you can go back to normal. We went through 800 meters, over 800 meters of hydrogen sulfide. To give you an idea, in the cores themselves was 140,000 ppm of hydrogen sulfide, and 1,000 ppm is considered lethal. We were in shallow water to compound everything. We were getting a core up every 15 minutes. It takes a full hour to process a core. So we ended up, you can see some cores down here now, we ended up with upwards of 24 cores laying on the floor because we simply couldn't process them fast enough. And and we looked like a bunch of beetles. It was hilarious. It wasn't funny at the time, but it was funny afterwards. Now, here we have the core lab on the Challenger, and this is our natural gamma machine, and that was about the extent of our physical properties other than sonic velocity. On the resolution, this is called an MST. We have magnetic susceptibility. We have a GRAPE, that's a gamma ray attenuation porosity evaluator. It's a highfalutin name, is that you pass a radioactive beam through it and you measure its attenuation, and then mathematics gives you all sorts of information after you make suitable assumptions. Keep this in mind because you will see an MST coming up. But all of this information is necessary because we now correlate all of our cores. It is necessary on the resolution because when we do high resolution studies, we have to drill up to 5 holes before we get an absolute recovery. Is that if you use the information from this, each hole is slightly different from the other, and you need to have everything, and they just kind of blend things. They have a composite section. Here is another view of the core lab, and that's the whole thing. On the resolution, it's about 4 times as big. Now here we have at the sampling table, but it's quite extensive. We're entering information into the computer, and it's very, very efficient, high productivity. These are our common sampling tools. These 3 items here, I would say we do 99% of our sampling for all scientists with these things here, from about 1 cc in sample size up to 20 cc's. Now, and again, you can see the sampling table. Now, you don't think of a label as a sampling tool, but in fact, this information right here identifies the core and identifies where the sample was taken in the core. This information here is the sample request number, and we can go back to the computer and find out what this person was studying. Just from this information here, we can get the sub-bottom depth. This little device here, the scientists love because they can use a scanner and enter the ID into their databases very quickly instead of entering it by hand. From the curatorial point of view is that when we get the sample back, we can retrace its history. So we have an idea of what may have been done to that sample. And I really enjoy this one here. In 1968, there was no such thing as a personal computer. And literally, much of our work was done using the calculations, using this. So we had a Olivetti programmable calculator that we could program up to 25 steps, but it didn't do very much. The Joides resolution, the only thing that they have more than computers are maybe sound systems. This is the user room here. A little sociological study here is that the fact that there's only one person here says that it's at the beginning of the cruise. And if you could see, he's asleep. Toward the end of the cruise, every computer will be used 24 hours a day, and there will be large mugs of coffee. There's nothing like the end of a cruise to get people rejuvenated to get their work done. But there's a few other things. Now, the business end of drilling. This was our original bit, a rotary bit. It was a workhorse, but it works by rotating, which is fine, except that in soft sediments it stirs the sediment. You lose all the structure. And at the beginning of the deep sea drilling project, that didn't matter. They were more interested in how old was the oldest sediment. But when they started looking at the continuous geologic history, that it became unacceptable. And so the engineers came up with this device here, which, by the way, you can see these things here. You can come up and touch the bits. This one here is a hydraulic piston core, and it's much like the piston core that Warren was talking about, except we use water power to push it in. And so we can recover undisturbed samples for 250 to 300 meters in depth, depending on how things go. When we we had several learning exercises. We used to think when we first started using it that we could use this bit, the hydraulic piston core, to where we couldn't push it in any further. After we left a few of the core barrels in the seafloor, we realized it was pulling it out that was the difficult part. And so when we get to a certain pull on the wire line that we recover the core with, then we switch to an extended core barrel, and this latches in, it replaces this head here, and it drills like a regular drill bit, in theory. This big bit here is its sole purpose in life is to help reset a re-entry cone. Not only are we interested in the upper part, but sometimes we need to go deep, and that requires re-entering the hole. So we will set a re-entry cone. It's a big steel funnel about 18 feet across, and on the resolution that we can re-enter a hole in 24,000 feet of water. So it's quite remarkable. Our deepest hole to date is 2.2 kilometers, and it's 504B, and that was started in deep sea drilling, and they continue to go back periodically. I think they've given up on it now simply because every time they go back to it, they end up leaving drill pipe in it. It's too hot. The metal is, they just don't have the technology just yet. Some cores here is that on leg 12 that I was on, here's a 46 million year hiatus. It was a big news. The scientists ran around. They didn't realize you could have such a large break in the geologic record in the seafloor because you should have continuous sedimentation. But in fact, yeah, while it's unusual, it's not necessarily rare. We have salt cores that we recovered from the Red Sea. Here's anhydrite, and this part here is salt. You can see the salt is more soluble than the anhydrite. Here, at this point here is the infamous KT boundary. This is where this 6-mile diameter meteorite struck the Yucatan Peninsula and caused the dinosaurs to go belly up, or facilitated their going belly up. Right in this area in here, what looks like dirt, and unfortunately the resolution isn't good enough for you to see here, there's little black specks, and that is part of the crust from where the meteorite struck the earth, melted the crust, and threw it into space, and this came down. This was drilled in the northwest part of the Pacific Ocean, so quite a few thousands of miles from where it happened, where the meteorite came down. But this subtle change right here, here the dinosaurs lived, here they were history. This is from our first hydraulic piston core site, and you can see how fine it is, and it's quite remarkable. And how do we store things? Well, it's the same as Warren, except because we use the same diameter core and we cut it up in the same lengths of time, and we don't get these big chunks of rock, we can have a very organized collection. We had to rearrange our cores I was getting closer to retirement. So when we rearranged them, originally all of the archive cores were on top and all of the working half. When we get the core up, we split it longitudinally, as you can see up here. Half of it is working that we sample, half of it is archive. Well, as you get older, you don't like bending as much. So when we rearrange things is that we put the archives up here and down here, and I don't have to bend at all to get out the sections. We modernized our labels. We have little buttons here to identify critical intervals and hydraulic piston core. Again, the barcode. We tried very hard to put barcodes on everything. In hindsight, I'm not certain why, because only the scientists seem to be able to use them. We haven't used them yet. But at least they're there if we want to. Now, that's basically the up to ODP, and now we're entering into what we call the Integrated Ocean Drilling Program. And it is a vastly expanded drilling program. And it's going to cover 3 continents and 2 regular drill ships, and then what we call a platform of opportunity. The riserless drilling is going to be the JOIDES resolution. And the upgrades, and we're just in this transition, they want to add 30 feet. Now, what's magic about 30 feet? From a pride point of view, is that the resolution is 470 feet, so that by adding 30 feet, they can say they're 500 feet. Now, my boss is back in back at the home office might disagree with that, but I think that's basically it. But they're going to expand. Importantly, they want to expand the lab space. The amount of science that they can do on board ship now is much greater than in the Challenger days. Now, the riser drilling is going to be managed by the Center of Deep Earth Exploration of Japan. The Chityu is going to be the ship, and it uses a riser, which the resolution cannot have, and that will allow them to drill where there's hydrocarbons, or if they're interested in going deep, that will allow them to go much deeper and case the hole to keep it from caving in. We have lost a lot of pipe by getting stuck from the hole caving in. And when you get a chance, you might want to come up and take a look at this, because you can see the results of what happens when you get stuck. Here we have the mission-specific platform. This is run by the European consortium, and their drilling program is to drill in areas that we can't drill with the resolution or with the Chityu. It is, they've already drilled in the Arctic Ocean and then off of Tahiti, shallow water, or where there's a lot of ice. And each one of those cases, it takes a special ship, and that's how they are handling it. All of these are coordinated as a single program. And it's all called IODP, the Integrated Ocean Drilling Program, and it's another layer of bureaucracy that runs the whole thing. It is a multinational organization, obviously, and it's done very well, the whole drilling program. The riserless drilling, I mean, we're still going to use the resolution. However, the practicality of having fuel increase 50% and the oil industry is monopolizing the dry docks, the management is having its challenges. So we need to stay tuned on that. But eventually, we will have a whole new lab stack, a much larger one, and it'll be quite good. Here is the riser drilling, the Chityu, Planet Earth in Japanese, and it's the only ship built from the bottom up as a deep ocean research vessel. They've spent $500 million building this ship. It is a huge, slow-moving ship, but it's very, very capable. Here is their core lab, and it's specially designed based on our experience in Australia over the hydrogen sulfide. It's designed for exploding cores. It's designed for gaseous cores. I mean, they have all sorts of safety factors built into the system. Here is their core splitting thing. I got these off of the web, so I'm not quite certain how this works here, but it looks a whole lot quieter than what we use on the resolution. Now, as a curator and as a sampler, this picture just terrorizes me. Right there, an inert sampling box. It is hard enough to sample when you have the cores out in the open, but to have to use gloves, inert gas, and such, I don't want to be part of that. No. Now, they have, I mean, welcome to the Mayo Clinic. The X-ray and the CAT scan, believe it or not, is that X-rays have a purpose, is that it allows the scientists to see internal structures and to see things that are hidden in the sediments that you cannot see otherwise. And I'm not quite certain how this is going to work, but it is a very big step forward. Now, I was telling you about the MST, the multi-sensor track where they measure all of these things. That is the Japanese version of it. Now, it looks very modern and such, but somehow this lid here, my feeling is that if this was installed on the Resolution, it wouldn't take long for the doors to be removed. I just see it as a problem. Microbiology, the big frontier in geology. We are finding bacteria where we never thought we would find bacteria before. I mean, on the Resolution, we have put in a microbiology lab, and we have done tests to see if there's drilling contamination of the cores. Unfortunately, there is not. But it is the effects of bacteria on weathering and changes in rocks are quite significant. There's, if you want to believe some people, is that some people are estimating that the amount of organic life that is in the crust equals that of the life that lives on the crust. So it's different form, of course, but it's quite an extensive thing. Final words. This could either be a sunset or a sunrise. Looking back, it is a sunset on a period of phenomenal growth of our understanding of the Earth's history and processes that make the Earth so unique. Looking forward, it is a sunrise with a very bright future, with 3 drill ships working on many different projects. It's going to have a tremendous effect on the growth of our knowledge of the Earth and its atmosphere. And I feel very fortunate as being part of it. Thank you very much. I think we're open for questions or darts, whichever wish comes first. The GPS, we don't use GPS, as a matter of fact. We use GPS to get to the site, close to it, but our positioning is by a transducer that we send down to the seafloor, and it sends out a very precise signal, audio signal. Underneath the ship we have 4 hydrophones that listens and times the arrival of the signal, and based on that they can calculate where we are, and then we can move it. Up until recently, the GPS was not accurate enough, and but even under the old satellite navigation, we were still able to find it. Now, in deep sea drilling days, we used, instead of a TV re-entry method, is that it was a sonar, and the re-entry cones have reflectors on them, and and it's also, these reflectors not only tell you where you are with respect to the re-entry cone, but it helps you find the re-entry cone when you first arrive.
When you leave the re-entry cone,
the re-entry cone is stuck there forever and ever, and one can go, if IODP or anyone wants to go back, they can. The advancements of studies are quite remarkable, is that they can plug these holes to seal it off from the ocean, and then go back and go through that plug and resample and retest the water, and it gives them an idea if there's water flowing through the crust, or if it is, how much of it is, and such. At 504B, our deepest hole, when we went back, they lowered logging tools. It just, I've never understood where they got the term logging from, but these are electronic tools that you can lower down and measure the temperature and sonic velocity, and you can do a world of studies. And when they first went back, as they lowered the tool down the hole, it kept reading seawater temperature. And everyone was scurrying around looking for their, where's the problem? And it turned out what was happening was that seawater was being sucked into the hole and into the crust. So it was quite an enlightening experience. You've hit a very tender thing for me, is that in a year after I came to work as a curator at the West Coast Repository, we had several earthquakes just off the coast. And that concerned me enough about how our core racks are built that I asked for a study to see what would happen, have an engineering study, but no one else took it quite as serious as I. I do know that the spot welds that are on the bars that hold the core up have snapped on some and such. Our hope is that when it shakes preferentially in a north-south direction. But unfortunately, we don't do anything. We just pray.
Thank you both, Jerry and Mara. Very much.